I guess, does anybody have a question?
How do the tokens work for the fire?
Okay. So I think what I'm gonna do is I'm gonna check the grade book after this and see if there's a quick way I can just see how many tokens you have left. I think so. I think through the grade book export, I can find that, and then I'm just gonna use whatever tokens you have. So it's not like you have to email me to tell me, oh, I want to use my tokens. I assume you do.
Oh, right, thank you. So are we just doing?
But I'll let you know.
Are we just doing like 10 to 2 points for the thing?
Yeah, that's it. There's no corrections or anything.
Damn.
Finally saying retake because.
No,
Oh.
that would be fair.
Less.
So.
Yeah.
We don't have time, that would be terrible.
I understand that.
Alright. You have a question?
I was gonna ask if you could go over orbital
Like chemicals? Like chemistry?
Yes.
No.
SP hybrid?
Yes.
I mean, that was cool too. Gravity.
I know.
Hey, technically you do also teach chemistry, so you never know.
Alright, actually, you're genius. So, so for what we want to remember for orbits. If this is like the planet or body you're orbiting, it has some radius of, call it planet. Then usually above that, at some height h, your object will be orbiting with some velocity. Sounds right so far? Okay. Now, what we want to remember is that in order to orbit, there's a force of attraction, universal gravity between the object and the Earth. But that for the Earth's mass is taken at, let's say, the center of any planet or object. It's taken at the center. So what we can think about is when we go to sum our forces in the radial direction, we have, we'll call this M1. We have M1 phi squared over r of the orbit. But r of the orbit, our orbit, is equal to r of the planet plus whatever height you are above that surface. Right, and that's why as you get closer to the ground, the speed required to orbit increases. And the higher up you go, the speed decreases. Is that good so far? Okay. Now this force is the force of universal gravity. And that is big G M1, we'll put in the mass of the planet, divided by r of the orbit squared. So that's the force that holds your object to the orbit. And so we plug in big G M1 mass of the, we can actually even call this capital M. Just to keep them really different. Over r of the orbit squared equals M1 phi squared r orbit. So the first thing we can do is we can solve for, we'll call this is v of orbit. So we can see that one of the r's cancels and the M1 cancels. So we see that v squared is big G mass of the planet divided by r of the orbit. Then you can just take the square root of both sides. And that is the v required to orbit at some distance above the surface. And so then if you think about, oh, as my orbit gets bigger, the orbit speed gets lower. If the orbit gets smaller, the orbital speed gets bigger. Now also notice if the mass of the planet changes for some reason, so does the orbit speed. Notice M1 is not in here at all. If M1 changes, the orbital speed does not change. So as I say, whether you put a large space station in an orbit at a certain height, or you put a smaller rocket in orbit at that height, they both have the same V orbit at that height. Now, the other part you can do is you can remember, since we're moving at a constant speed, you can remember that we said velocity is distance over period, where t is period. And our distance, of course, is 2 pi r of the orbit over period. Right, because you're running a circle, 2 pi r, in this amount of time. So what's really easier to do is easier to go back to the squared form of this. So if we go back to the squared form, we'd have v squared is equal to big G, big M, planet R orbit. Now if we square this, we have v squared is 4 pi squared r squared over t squared. Then when we substitute that in here, you get 4 pi squared r squared t squared is big G, mass of the planet R. And so we can rearrange this to see that t squared is equal to 4 pi squared r cubed divided by big G, mass of the planet. So that tells you the orbital period goes with r cubed. And as the mass of the planet gets bigger, or whatever you're orbiting, the orbital time gets, because you're going to run faster. Those are our two orbital equations. 5 and 4. Avoid that window.
Want somebody to close the door?
I don't know. I guess you could. Is that okay? Did that answer your question? Yeah. And side note, this is technically a standard thing you'll see in orbits, or even when we talk about like roller coasters, Ferris wheels, cars going through dips or turns, or anything with our circular motion. The M1, the mass of the object, usually will cancel on a lot of these equations. So usually the mass of the object cancels out. That's it. Oh,
Can you do something with like the parent weight, like an elevator or a hill or something?
sure. Can I erase this? No, I don't. Sure. So, if we're thinking about the elevator. No, this is here. So if we're thinking about the elevator, there's a whole bunch of cases, so I'm just gonna do like one, and then you can reason out the others. So we have somebody in an elevator. And as most normal people do, they bring a scale with them, right, and they go to the elevator. And this way they can track their apparent weight. So we remember that the apparent weight always comes from the normal force, right? So we said the normal force is your apparent weight. It's how you experience your force. And it's only found by summing forces unless they give it to you directly in the problem. So when we're thinking about summing forces here, we sum our forces in the y to get MAY. Now, in general, what we see is N minus W is MAY. Now, there's a bunch of different cases, and this is where you have to think about the kinematics in terms of what's happening to the elevator. Because based on what the elevator's doing, you will get different accelerations. So if let's just say they tell us the elevator starts from rest and accelerates upwards, or it's increasing its speed upwards. Well, that would tell us that A is upwards. Right? And if A is up, that means this AY term stays here, and N is W plus MAY. This is if A is positive. Is everyone okay with that idea? So now A can be positive in several different ways, but when A is positive, this is your result. You feel heavier. You feel like you're being pushed down into the floor of the elevator. Now the other one you can have, if you're thinking about this again, you can have somebody standing in the elevator, but let's say now you're moving downwards, you're moving upwards, but they tell you you're slowing down. Right, so if V is up, but you're slowing down, right, that would imply that A is down. So this time when you sum your forces in the Y, you get MAY, but you have normal minus W equals, in this case, negative MAY. We're just assigning the negative to the AY. And then we see it's W minus MAY. You feel lighter. And then the third one is if you don't have any acceleration, like if the A could be 0, like if you're moving at a constant speed, A is 0, and then you're just your weight. This is actually, this simple thing like this was what made Einstein think about general relativity. Like he thought about if someone was in a sealed system and they were accelerating upwards at 9.8 out in space, they wouldn't know if they were in an elevator on Earth, except like on a floor on the Earth somewhere, or if they were out in space, they would have no idea. Right, so he realized that like acceleration is just like a manifestation of space. It was like one of his movements forward in terms of understanding gravity. So people wouldn't notice the difference. Is that okay then for your elevator? Yeah. Okay. And like I said, then there's lots of, I forgot how many, there's like 4 or 5 different combinations. Oh.
Can we go over like moments of inertia and angular momentum?
Yeah. Now, do you have a specific problem? Or no?
Like on the concept review, it was like a merry-go-round spins freely when a stick person moves quickly to the center.
Sometimes it's Diego, sometimes it's Stairs.
It asks like, does the moment of inertia increase or decrease?
So, okay, so you have this merry-go-round, and is the key on the outside or inside to start?
Outside.
Outside. So here's our friend stick person, and this is, it's rotating with some omega. The wheel, the disc is spinning with some omega, and then he runs inside, right? He runs to the middle. And then he's gonna move to the inside on some line that doesn't affect any blah. Anyways. And what's the question?
Does the moment of inertia increase or decrease? And then does the angular speed increase or decrease?
Okay, so we remember that inertia in general is related to mr squared, right? In general, this isn't any, I put a twiddle there because this is the general concept. It's related to mass and the distribution of the system. Now, if we have multiple objects, then let's say this system we have, this is going to be I of the disk plus the I of a point mass. And the person is treated as an object, like a blob of clay on the disk that moves around. Because he himself is not spinning on an internal axis, he is part of a system that is moving around. So he is like a point mass sitting on the disk. So initially, when we think about the initial I of the system to start, we have I of the disk plus, if we just think of this as mass of the person, radius of the disk squared. Now, at the end, when he moves in, let's just say this to end. You still have I of the disk, but now you have, let's say, mass of the person at 1/2 R of the disk squared. So let's just say he moves in, somewhat, not all the way. So is this I bigger or smaller than this one? This I is, yeah, so ISE is less than ISS, right? So the initial moment of inertia is bigger than the final. Now, when we're thinking about angular momentum, L of a system to begin equals L of the system N, where we remember inertia is I omega. What we think about is we have I system initial omega, start, sorry, and omega start has to equal I system N omega N. Now, because this got smaller, so these two have to multiply to be this number. Because this got smaller, this has to get bigger. So the speed should be larger when the person walks in, just like when you have those ice skater problems and the person's like spinning and then they pull their arms in and they speed up. It's the same thing, except this time it's somebody on a disc to change the moment. Yeah.
Yeah, I understand that like mathematically with the equations,
Uh-huh.
but if you're standing on the outside of a circle that's spinning,
Mm-hmm.
are you gonna have to be going faster to get from point A to point B than if you go to the middle to get to point A to B?
Yeah, that's what I'm saying, is you're just gonna assume you don't worry about like the friction losses to the disc while you're moving in.
I'm just saying, like, if you're comparing like person on the outside to the person on the inside, if they
Right.
both, if the disc spins the same amount, isn't this person on the outside gonna be going faster than the person on the inside?
Well, he's walking in. Yeah, so he'll be moving, he himself will be, but the system will have a new rotation rate when he's done walking. The system's rotation rate will change. Yeah, so this person will be spinning at a different speed because the disk system will change.
Wouldn't the speed on the inside be less than the speed if you were standing on the?
Yeah, but it's the velocity maybe, but we're caring about omega, the rotation rate. This person's velocity will probably, but the disk will speed up also. The rotation rate will get larger. You'd actually have, if you wanted to get down into the nitty-gritty detail, you'd have to actually look at the number, but in terms of the angular speed, he will be moving faster here angularly than he will on the outside. Because remember, he's gonna sweep out angles, not distance.
So linearly. the
You'd have to
outside-
actually solve the problem to calculate that out.
The outside person travels more distance, but the inside person completes a revolution
Yeah, but the disk
faster.
has changed speed, that's the thing. You have to actually know what the disk changed speeds to, omegas, right? So the rotation rate changes, which means the V at the end will be different. So the rotation rate is different at the end, it's higher. And you can't make a claim about velocity without knowing the numbers. Because if the disk has a much bigger inertia, the person's speed will change some. Depending on the distance of inertia.
Would you be able to go over the 6 categories that you just said? What are those 6 categories
Oh,
that are
you
gonna be
mean
your?
For the elevator,
No. For your extended response questions. We did not get that.
oh, it's on the sheet, did you share the sheet?
What sheet?
Oh. Can I erase this?
Yeah, go for it.
Go bananas.
I heard the names. Alright, it's not. So, so,
And then a few like examples. for also.
they're all in your book.
Oh, that's such a help. That's so much. Now you're starting to sound like a chem professor.
There's 1300 alright, so when you think about the semester, at least how like my course was set out, because I don't, you guys had your exams at different points. Like the first thing you probably talked about was, what did we talk about? Motion, right? We talked about motion. Right? And the big three out of motion, the big three equations you care about out of motion are, of course, V final equals V initial plus AT. V final squared is equal to V initial squared plus 2A delta X. And delta X equals V initial T plus 1/2 AT squared. And this allowed you to solve motion problems with constant velocity, accelerations. You could break it into 2 dimensions by separating out your stuff. And of course, then you need all your vector stuff too. But this allows you to solve projectiles and all that good stuff. Next up was it's lost. And the big one, the only equation out of this, F equals ma. Now you have to remember the forces, like all the forces in the catalog that are listed in chapter 4 and know how to apply them into here. And the thing to remember as well is really when we talk about this, because of the component nature of forces, you really do a sum of forces in the x and the y. You break all your forces into components, and then you add up the components. Remember all the cool things about accelerations in terms of if it's moving at a constant speed, oh yeah, my A is 0, like that kind of stuff. Anytime something moves across a surface, acceleration in the y is 0. Those kinds of things are good to remember. Yeah.
For something that says it has like constant velocity, say it's like going through the air or something, is AX always 0 and AY 9.8?
Yeah, so back here in the air, when you're moving through the air, you remember that AX is 0 and AY is G and its direction is downwards.
The AY is 0, there's like.
It's only when you're on a surface.
Okay,
Once you're in the air.
Yeah.
Your object will not have constant velocity. Unless it's falling at terminal speed. Right?
okay,
Unless you have to worry about drag. Like they would tell you, oh, it's falling at that one problem, like the guy falls, it's I don't know, squirrel or something. Anyways, so and then also with this, he said you can sum forces in the radial direction if you're moving at constant speed in a circle, right? And that led us to like our roller coasters, going over hills, through dips with cars, taking turns in a car, all that good stuff. This is the general idea of this involves summing forces. And you have to be able to draw force diagrams. Right, you should be able to draw pictures. Third, this is related to the second law in rotational form. This is the sum of the torques is I alpha. All right, where it's tau, this tau is the torque, and torques are RF sine phi. So you have to be able to calculate a torque. Remembering that this is not a radius, this is a distance force applied to the pivot, right? And this angle is between F and R, the force and the radius. Now I is the moment of inertia, and those would be either given to you in the problem, or if you don't have them written on your equation sheet and they're not on the problem for some reason, you should just ask, and that should be given to you. You're not supposed to memorize moments of inertia. All right, but moments of inertia, as we said, the idea is for moments of inertia, they depend on M and the distribution, mass and the distribution. And I use the classic example of my pen, my marker, because my marker can have, like just based off of the book in the table and book, this has 3 different moments of inertia. The first is if it's just rolling back and forth, it acts like a cylinder. It acts like a cylinder rotating through this axis. That's one moment of inertia. If I spin it like this through the middle, it has a different moment of inertia. Then it's like a little helicopter blade rotating. The last one is I can swing my marker like a bat on end. So it's not just the mass of the object and its length, it's the mass and how we rotate it. Right? Is everyone good with that? So those are our moments of inertia. And those, like I said, there's a list of them in the book. You should, if you don't want to write that on your equation sheet, then you should hopefully it's on the text. You can ask if you. And then alpha, of course, is the angular acceleration. And then we can rewrite 3 equations of motions in terms of theta, omega, and alpha. All right. Number 4, this was going to be momentum. And there's a couple things with momentum. First off, we said that momentum P is mv. Then we also said, did the book use I or J for impulse? J? We'll use J, and that's equal to force average times time. So the idea would be that a force times time causes an impulse, and an impulse, we said, changes the momentum, right? And that led to the impulse momentum theorem, that the average force times time is the change in momentum. Then that also led us to, if you wanted to use the 3rd law with this for interacting objects, we said that momentum is conserved, so P of the system before equals P of the system after. And we said that the system, with the momentum of the system that is conserved, the individual objects in the system, their momentums can't change. Then we also could repeat this for rotating objects, and we said that we have L is equal to I omega, that's angular momentum, and we said that L of a system, as mentioned just a minute ago, before, equals L of a system after. And in what type of collision is momentum conserved? All collisions, right? All collisions, momentum is conserved. If you have a collision, you conserve momentum. Then category 5. What's your category 5?
Energy.
Energy. Category 5 should be energy. And for energy. We said that we had a bunch of things that go into our equation. We said that work is Fe cosine theta, that the work done on an object can change the energy of the object. We said we defined the energy of our object as kinetic plus gravitational plus elastic or spring, such that work changes the energy, and then we also said it could change the thermal energy, with the thermal energy being the force of kinetic friction over the distance that it happens. And then we can break this apart into all kinds of things like energy initial plus work equals energy final plus delta E thermal. Then you can come in and break these into more pieces if you want to. But that's the concept of energy conservation, right? And then we also had power as well. And then the 6th one is under fluids. So we had pressure in a fluid is rho g depth or y. We then had buoyant force is rho of the fluid g v displaced. And then we had the Bernoulli's equation, P, not P, but P1 1/2 rho V1 squared plus rho G Y1 equals P2 plus 1/2 rho V2 squared plus rho G Y2. And that was Bernoulli's equation. And then we said, just like we had fun in the lab, we did that. We said that, oh yeah, you can have some kind of like tension, buoyant force, and weight. So when we summed up our forces, we had tension plus buoyant force minus weight equaled MAY. And we noticed that the tension in the string can vary depending on, is the object like accelerating up, accelerating down, being held at constant speed, not moving at all. Like the tension changes also because of the buoyant force. And we saw that the weight was the force on the tension out of water, and then dropped it in into the water, and the tension force dropped. Does that sound like something we did? Maybe. But those were our fluid equations.
You do the beetle jumping for me.
I'll wait till everyone's done top.
Gets me every time.
Yeah, is it about him?
No, it's just a good problem.
Was it?
It is. Those students makes you think. Has everyone got? Is everyone good with this? So there was a request to do the beetle jumping process. I assume it's jump. Is it one where you go straight up, or do you launch it and hang?
Do it again.
Those are harder.
Yeah. Either one.
Is it the problem?
Maybe I should have known if I
Oh.
whatever they were saying.
Yeah, you really forget. She's looking up. Yeah. Sure. It's up to you.
I'm reading all the numbers.
That's fine.
Just gonna get to something.
It's a good one. You, looks like you solved it.
Yes, I just guessed.
Oh,
But I got it right.
alright, so it says a car is traveling north at 17 meters per second. So there's some V, it's 17 meters per second, and that's north. It says after three seconds, its velocity is 25.1 meters per second in the opposite direction. So T equals 3 seconds have gone by, and now V is 25.1, and it's in the opposite direction. So we'll call this V initial, and this will be our V final. And they want to know the magnitude and direction of the car's average acceleration. So we remember that velocity final is velocity initial plus AT, or you could say that A is delta V. Either one will get you to the answer. Now, what we have to remember is this is going to be V final minus V initial over T. And so we see that if we're going to count this way as positive, then this one has to be negative because the direction has changed, because these are vectors. And so what we see is this is minus 25.1 minus 17 over 3. 42 divided by 3 is about 14. So A is negative 14 meters per second squared. And that would be south, because negative would imply south. You're good? Okay. And you found your bug?
Found a bug.
Oh. An R beetle? I find one bug that was really cool. It's like some bug that sprays like acid or something and can do it like really fast.
I thought that is about that.
Did I put that on something? The
Yeah,
bug spraying
I thought
acid.
I think that is the counter beetle.
I found like the video. It's like they spraying the ant from the store.
Okay.
You got it? Alright, sorry. One second.
Oh, I was distracted.
Oh, no.
You go for it?
Well, he was in. What's up?
Certain insects can achieve seemingly possible.
Right. Seemingly impossible accelerations.
While jumping, like beetle accelerates at an astonishing 400 grams over a distance of 0.59 centimeters.
100 G's.
Yeah, gee, oh, yeah.
Over what?
Over 0.59 centimeters. And then, assuming the beetle jumps straight up, at what speed does it leave the ground?
So we have this beetle that looks just like a stick person. And the idea is that this beetle,
Just give it another set of arms and then it's a beetle. There you go.
so we have our stick beetle, and the stick beetle starts with its legs, a delta X of, let's say, 59 times 10 to the minus 4 meters. They told us 0.59 centimeters. So then after it extends its legs that it's using to jump, it's going to leave the ground with some speed. So V initial is 0, so like when the beetle is crouched, then it will extend its legs that distance. And it will leave the ground with some mystery speed. Now they tell us the acceleration is 400 Gs, which this tells you that's 400 times 9.8. Remember, G in this context isn't a direction, it's a value, 9.8. Because that's how hard he's pushing up off the ground during this distance. So they don't give us a time, so we can't use, most people really like to use this equation or the other version of it. But notice they didn't give you a time. So when you're not given time, you need to switch over to your time independent equation. And now you can solve for V final directly. So V final, for the speed he leaves the ground with, squared is equal to 0 squared plus 2 times 400 times 9.8 times 59 times 10 to the minus 4. So it's almost 6.9. Okay. As a count. What? I think it's like 6.9, 6.8 or something. I got 6.8.
So it's almost the same as gravity. Almost. Not really though.
Is that fun? Then you can actually calculate how high up you go, and how much time was the beetle in the air, all the good stuff. Yes. Oh, what? Do you have a fluid problem? Oh, I'm not gonna. I've made up enough problems. Making problems.
He said, I'm tapped out and I'll see you all for final.
I made enough.
I was asking if she had anyone break down what you did on the board.
Like when it's principle, like I have like a tube and water's going through it.
Uh-huh.
And the tube like expands.
Uh-huh.
And I like draw it, it explains what's happening.
Yeah, simple answer, and say, no. No.
It's all right. So someone asked about, like if you have fluid moving through a tube. And then the tube expands. And I would say that the first way you should look at trying to solve this is, let's say you have some fluid moving at some speed. And then it changes. The idea would be that if they give you, depending on if they give you R or D, like they give you the radius of the diameter, remember that the radius is E over 2 if they give you diameter. Remember, that's important. Otherwise you'd be off by like a factor of 4. Then the idea would be you have some, you'll call this R1 here, R2 there. Now, if they give you the velocity here, and they just want to know the velocity here, They give you this, sorry, not this. They give this to you at some number. Then you can just use the continuity of flow. You don't need to pull out Bernoulli's principle. The only time you have to pull out Bernoulli's principle is if there's like pressure. If they mention pressures, then you need Bernoulli's principle. But if they just tell you velocities and radiuses or diameters, you can use continuity because A1 V1 equals A2 V2. And sometimes you even need to use that in a Bernoulli problem to get one of the V's if they only give, depending on how much information they give. Like if they don't give, let's say they give you this and they give you a pressure, you need to find the other pressures.
So would this be for like a syringe? Like,
Yeah, so I would use this for the syringe, yes. Right, because the syringe, the fluid is changing from the thing to the little knot, the little needle. And that's where you can use the. Yeah, it's okay.
so, well, there's another one, it's like, alright, like there's a tank and it has water in it and then water comes out like a spigot
Yes, we did
and it
that.
asks about like the pressure and the rates. You wanna see it?
Sure. Did I sign this?
So it's on the thing. Mass trains.
Man, why would I sign this? Oh, you got it right though. You should explain.
AI help.
Do you need me to solve this completely or just conceptually?
Conceptually is
Okay, yeah, so, so this is similar but different. Is pressure one, do they give you pressure one? No, I think it's exposed, isn't it?
Yeah.
Open tank, yeah. So the pressure at the top is P0. So two. So they give you this area, they give you area 2 and like area 3. So what you can do is you use you can use the fact that gravity changes the energy to get the flow rate, I believe, using Bernoulli. And then once you know the velocity here, you can calculate the discharge rate of the water. Then you can use Bernoulli's principle to get the gauge pressure. Is it?
Actually, do you mind going all the way through it?
I'm trying to pass.
Oh,
Yeah, so I think this is like a bed, and this is like 8, I meant 2. So you have, because here and here are gonna be at the same pressure. That you can basically just look at rho G Y2 minus Y1, or in this case, it's gonna be 10 minus 2. And that's just gonna be equal to 1/2 rho G2 squared. Then I think once you have this, you can get the velocity at 3 and get the flow rate, then go back and get the pressure. Yes. Does that make sense?
Yes.
Awesome. Hopefully that's. That's a pretty big step up.
Pretty long was my step problem that one should expect to be an extended response, or it's too long to be seen as an extended response.
Oh, that looks pretty long.
Noted. Noted.
Okay.
Yeah, I can say, are the tests for both classes the same?
They're very similar.
Okay.
The tool is exactly.
I mean, the answers can be in different places, questions can be in different orders.
Yes, but.
Should be on page.
You get, can we do that? I want you from, I have it here.
So you're in the bugs.
Oh, well, right.
Something not healed.
Really not, just so we can.
Yeah, thanks tomorrow. What?
Give me the answer. You gave me the answer.
Yeah.
All right, so we have this spider that jumps.
Recovery.
Spider.
Alright, so we have some spider that's gonna jump. And they tell us this spider is jumping at an angle of 52.7 degrees.
That's really.
And it launches with the speed of the initial is 3.07 meters per second. They ask, what is the maximum horizontal distance that you can cover? They want to know delta x. And they want to know the maximum height. So the things that we want to remember are that in a projectile, AX is 0, AY is 9.8 meters per second squared down. Put the negative in how we see fit. We know that we remember at the top here, Vy top is 0. And then all we need to do is break our velocity into components x and y because the accelerations are different. So we remember that Vix is Vi cosine theta. So Vix is 3.07 times the cosine of 52.7. Seems like enough.
1.86.
1.86, thanks.
It was supposed to.
Alright. So this is Vix, and then we know Viy is Vi sine theta. So Viy is 3.07 times sine of 52.7. And so Viy times like 2. That's not big.
2.44.
2.44. Now that we've broken our velocities into components, now we can separate out and solve our two different problems. So because we're leaving the ground and going up and coming down, all we have to do is find everything at the top for the time and the y max, and then we can just double that time, and then we can find delta x. So to find, we can find time up first, because we can use Vy final equals Vy initial. And now here's what we have a choice of. If we plug in positive ay times time, then we have to remember to put the negative in. If we call this minus gt, we've already included the negative. We don't have to double the negative. So here we know that it's 0 equals 2.44 minus 9.8 t up, where we're looking for the time up. Or time to the top, however you view it. Six.
0.25.
0.25, thanks. So t up is equal to 0.25 seconds, which means that t total, we can come back and get this in a minute, is 0.5 seconds because of symmetry. If the bug launches from a cliff or something, then we would have to solve for t down. But because of symmetry, t total is equal to 2 times t up due to symmetry. Now we have our choice now of equations to find y max. We can use either delta y is equal to VIYT plus 1/2 AYT squared, or you can use V final squared equals V initial squared plus 2 AY delta. I think we should use the time independent one, because if we made a mistake on the time, then we might propagate it into the next calculation. So let's try V final y squared equals V initial y plus, or we can call this minus 2g delta y. And here then we have 0 equals our 2.44 squared minus 2, 9.8 y max minus 0. So y max is just 2.44 squared divided by 19.6. What do we do?
0.30.
Okay. Then define the horizontal distance, delta x. All we have to remember is that delta x equals VIX times t total. And delta x is equal to 1.86 times 0.5. Inch 0.93.
Could you go over like I don't have an exact problem with like numbers, but it's just how you would find like the coefficient of static friction. Like if you had certain forces or whatever.
If it look good with this. So you want to find the coefficient of static friction.
Yeah.
Are we on like a hill, flat surface?
We can do a hill. That's what it's called.
Is there anything acting on the block or is it just sitting on the hill?
It's just sitting.
Okay. So let's say we have a block sitting on a hill. And we're tasked with finding the coefficient of static friction. So they tell us that no, let's do it this way. We're gonna put something pushing, because
Okay.
that's it's a better problem. All right. Let's say we have somebody pushing with some force, and they tell us that this person pushes with a certain amount of force that just breaks static friction, and they want us to determine the coefficient. How does that sound? Alright, now what we want to remember is that we need a normal force this way. Our weight vector works straight down. Wrong spot. It goes here is WY. This is W, and WX is there. Then we also, because we're trying to break static friction, we have the force of static friction right there. So we then remember that WX is W cosine theta. W sine theta, and WY is W cosine. And then we remember, because we are just breaking static friction will be at its maximum value, U static 1. Is everyone good? Okay. So the first thing you have to do is you have to sum forces in your Y, because because you need to find the normal force in order to calculate the part of the friction. So we see that normal minus WY is equal to 0 because we're moving parallel to a plane, so AY is 0. So we see that the normal is WY. Now the next part is we can sum our forces in the X, and we have MAX. Now what we're going to do is we're going to say that we're just breaking static friction. So the idea would be that the sum of our forces is just going to be bigger than 0. Right? It'll just be slightly larger than 0. But what we see is that it's FP minus WX minus force of static friction equals, or this has to be just larger than 0. Or what we see is the force of static friction is going to be FP minus WX. And because they gave us this and we know the mass of the box, this is a number. And so we see that mu s times the normal is FP minus WX, or mu static will be FP minus WX. In that case. Do you like adding vectors? Yeah. Okay. Is everyone okay with this? Okay. Let's say we have. You have a preferred two vectors we're gonna add. Like, is it gonna be A, B, or do you want A minus B? Do the quadrants, do you want them in?
A minus B.
Alright, so what quadrant is A in? Quadrant two, and you have a length and a preferred angle.
Length 5, angle 30.
30 this way? Like this way 30?
Yeah.
Okay. So here we have some vector length 5 and an angle of 30 degrees. This is our vector A. And where's B? What's vector?
Hold on.
She's all real numbers.
Vector B would be what? The last bottom.
This
Yeah, that one.
Okay.
And it's 8.5,
Okay, at what angle?
45
And
degrees.
that, oh, doesn't matter. So this is 45 degrees at 8.5, and this is vector B, and you said you wanted A minus B.
Yeah.
So now what we remember was whenever we're gonna subtract vectors, really, that's like adding a negative B. Right? So it's going to be A plus a negative B. Where negative B then is really at 45 degrees up this way because it's flipped 180 degrees. Right? So now vector B is up here at 45, and this is our 8.5. You good? Okay. So what we remember then is that this would be R, where we have to then make our Rx, Ry, such that Rx is AX plus BX now, because we've already accounted for the negative. We've put the negative in, and then Ry is AY plus BY. Now, the other option is you can calculate the components right here and then add the negative signs as needed. You can do that either way. You're good? Okay. So then AX, we see that AX is going to be 5 cosine of 30, or, so here's where you have to start being very careful. You have to decide if you're going to put in cosine of 150, or are you going to put a negative in here and put cosine 30? Because you have to account for the fact that it's pointing to the left in one way or another. So we'll put in cosine 150, and that'll take care of our negative. Yeah. Then we have our AY, and this is 5 sine of 150. I did that one more, please. So let's remove this over. Just here. So AY is 5 sine of 150. And so we can get a number here and a number here. Then we also see again for this one, again, BX. This is 8.5, and because BX is pointing to the left, we have to make sure that we take 135 for the angle to make sure we get the sign right. And then BY, again, is 8.5 sine 35. Then we need those numbers. So we can say that Rx, we can then find our Rx and our RY.
AX is negative 4.3. AY is 2.5. Negative 6 for BX. Six as well.
That's 45.
Yeah.
Alright, so Rx then is negative 10.3. And Ry looks like it's 8.5. So then the new R vector is the square root of Rx squared plus Ry squared. So R is the square root of negative 10.3 squared plus 8.5 squared.
Four.
Okay. You good?
Yeah.
Okay. So the
So why we
angle
haven't
is
done-
just
Yeah.
Ry over.
Yeah, we just have done those more. Very quick in this room. It says very quick in this room.
Oh, because the sun's good. They don't, maybe they don't have the heat. Yeah.
Can you do this work problem?
I think you're in.
The ice. Someone's asking for like a percentage or something.
Did I assign this?
No, it's in the book.
Yeah. Yeah, this problem isn't anything we talked about. We can do it, but we have to use the Young's modulus to calculate F max of the muscle.
Do you want me to find one that's?
I mean, I can just do the bicep problem if you want. I mean, I can do the Young's modulus, but that's not on the exam. So I don't know if that's a good use of it.
I don't even remember what that was, so.
We never talked about Young's modulus.
Okay, cool.
But do you have numbers?
I mean, I can just use these and then make up a number.
Right.
Yeah, add a number.
Oh, yeah.
She spent like 10 minutes on that slide.
All right.
I was just.
All right. So we're gonna look at the bicep problem again. So there's our elbow. They tell us that this tendon is 0.04 meters. They tell us it's 4 centimeters away. They tell us that someone's holding some massive 110 kilograms in their hand. And that this is 35 centimeters or 0.35 meters away. And they don't mention the mass of an arm. Oh, they're lifting half the weight, so they must be doing, sorry, this is 5. Sorry. They don't give us the mass of the forearm in this problem. You want to put the mass of the forearm in? Yes or no?
No.
Okay, so the idea then is when we look at this problem, if we're holding the weight stationary in our arm, we know that this is a rotational equilibrium problem because the forearm can move as though it's on a hinge. Right, so it has the capability of rotating. And so what we need to think about is what are the forces and what are the torques acting on this forearm. Now, when we first go look to sum the forces, so they want to know what's the force in the tendon. So we'll look at the force in the tendon. Now, initially you might say, oh, the force in the tendon is equal to the weight in the hand, but that's wrong. Because when we go to sum our forces in the Y, we have MAY. Now, we have to remember that there is some force of an elbow somewhere in there. Whether it's plus or minus, we're not sure, but there is a force of an elbow in there. Probably minus, but then we have the force of the tendon minus the weight in the hand, and those add up to 0. Because of this unknown force, we can't just sum forces directly. All right, so there is some elbow force that we don't know. Force elbow. Now, what we can do though is we can sum our torques and we can put our pivot at the elbow. So anytime your pivot is the location of a force, it doesn't contribute to the torque. So now when we go to sum our torques, we have torque equals I alpha. They tell us we're holding the barbell static. So what we see is we have the weight in the hand and the force of the tendon. And so we have the torque from the tendon, which would be, it'll go counterclockwise, so it's positive, and the weight in the hand will cause a torque that is clockwise, so it's minus the torque of the weight. Those add up to 0 because the arm is stationary, it's not rotating. So what we see is, it's not that the forces are equal, it's the torque provided that is equal. So we remember that the torque is RF sine phi. So what we have is we have the radius to the tendon, the force in the tendon, and then the angle is 90 degrees. So it's 1, so it's sine of 90. And that equals the radius to the hand, the force, the weight in the hand, times sine of 90. So what we see is that 0.04 times Ft equals 0.35, 55, 9.8. Or the force in the tendon is 0.35, 55, 9.8 divided by 0.04. Probably 4,500. I would add it. Gee. 47, 60, 47. It's free laptop.
I need a new one, so.
Thank you.
Yeah.
Can you do it
Oh, wow.
Oh, even grass.
They did that.
Oh, did you guys not?
No, we never did any better.
Oh,
We were just told humans for 25.
I was like, it's had 2 weeks.
We did one day.
Yeah.
One day.
It felt like a while.
Yeah. Is that,
Time is irrelevant.
This is metabolics not on, right, it's not on that sheet I gave you.
Is it not?
I'll do the problem, I don't mind.
I mean, if you want to, we still have to.
That's up to you. That's all.
There's a lot of tokens, yeah, there was a lot of tokens on that.
It was like 2 or 3.
It was like 6.
Oh, really? No, because there was the carrot, the banana.
And then it was people
Oh,
using
yeah.
that, but then it was like people using their metabolic energy.
Those are the 2 star ones too.
The star,
I don't know any-
the star ones were in fact radiation, and gravitation.
Is that how you were supposed to do those? Cause we gave up.
Right? There's another one. It's like-
Which one? The other cow problem?
The other, yeah, the other.
The other one radiation. Yeah, the radiating cow?
Yeah, or this one.
It's up to you.
Will you do this one?
No.
No?
Oh,
Okay.
All right. So we want to look at Stig Gunther. And Stig Gunther, he holds the world record for falling the farthest distance from a crane. He's from Denmark. So,
you learned about those. You knew those for free.
so they tell us that he starts 103 meters off the ground.
But you can create.
And they tell us that initially there's a cushion that he's gonna hit. That's 3.1 meters high. Then after and the cushion has a K value equal to 11,071 Newton meters. Then after he hits the cushion now is 1.9 meters high. And what they want to know is what speed is he moving with when the cushion is that compressed? Oh, and we know his mass is 78 kilograms. We assume he starts from rest on the crane and the crane just drops it. Is everyone good with that setup?
Yeah.
Okay, so this is an energy problem. We can solve this using conservation of energy. And what we can do is we can call this energy initial here and energy final there. So what we can do is we say, okay, our energy initial will ask, are we initially moving? The answer is no, we're sitting at the crane's holding us, right? Then we ask, are we above the ground? And we say, oh yeah, we're 103 meters above the ground. So we do have some MGY, which is 78, 9.8, 103. All right, and then initially, when we look at the spring is fully open. There's no, it's not compressed at all. So initially, we have no spring energy. Now, energy final down here, when we look, we say, okay, am I moving? Well, yeah, that's what I'm looking for. So I am. They asked me to find that. It's fine. Now, are we above the ground still? Yes, we're still 1.9 meters above the ground. So we have some MGY final, which is 78, 9.8, 1.9. That's 55. What is it?
1,452.
Oh, okay. 1,000 what? 452? Okay, there we go. Now, the spring is there, right? And so the spring is US final. That's 1/2 K delta X squared, or X squared. But we remember that's the difference squared between these two numbers. So it's 1/2 of our 11,071 times 3.9 minus 3.1 minus 1, sorry, minus 1.9. Gosh, 1 times, like that. Right, because it's final minus squared, so you can just take the difference. Even if it was negative, you square it. You get a number for that? That was probably 5,500. Pretty high. Huh?
It was something like that.
Like 5,539. Is that close?
I got 7,170.
That's what I.
That's what I
7,000? Okay. So maybe. 7,000 what?
971.
971. So now what we say is, we ask the two questions. Was there mention of work done by external forces? There is no mention of external forces in the problem. So we know that work equals 0. And there's no surface that is mentioned that we're dragged across for thermal. So we know delta E thermal is 0. So when we write our energy equation, we see that energy, we can write Ki plus UGI plus USI equals K final plus UG final plus US final. And so this is 0 plus the 78733, that's 0. And this equals 1/2 of 78 V final squared plus 1452 plus 7971. And then you subtract these over to the other side. 9,000. I think that's right. I don't know. Don't have the difference of these two.
42.
Huh?
42.2,
For the B final?
yeah.
Four point two? 42.
42.
Oh, you said, wait, no. That's right, that's right now, though.
Yeah.
Are you looking at it? Yeah. I'm looking at it. I didn't know her like 40 still about, I mean, they walked to me. She came out of groups, but not my actual grade. They went like 4 days.
That was the shoes. I don't know. What was it? She said she was still. She said she was.
So the last one, wasn't that bad? I mean, I know mine was, but I don't know if everybody else. It's like 7 years ago.
The way they shoot. And it's not like.
Thank you.
The second one wasn't good.
The
first one.
And the first one.
She didn't wear a curve.
She says.
Still don't understand how you can take away a curve
Why
from
we're
half
still
the
there.
guy. That doesn't make sense. Oh, yeah. Yeah, you can never really tell the difference. That's why I don't know. He's been doing them. Just 1 minute. See you. Oh, no, no. Final? Okay. Okay, whatever. That's what I'm saying. Wait, you got that. Because my group is educated, but my grade itself is not. I said, we had to give it back.
We're gonna have a week of health problems.
Did you see how many on the flannel that you put?
No, like this semester, I gathered when every health problems passed. That was actually.
I like 6 cow problems and at least 3 chickens. And all of us were just saying that going, why farm animals?
Because most of you guys are in that.
I like cats.
And they get.
Okay, maybe that's just a me problem then.
I know, like, I never hear about people doing like sheep, like taking their sheep to the sheep show, but I always hear about the cattle team. I never hear about sheep.
I think,
I never heard about.
I think because we did density and capacities.
How's are more?
How's are more gross.
They're like 1200.
All right, so it says that this cow, they have this cow that's in the run bear. And the cow was running like a circle.
Oh God, not this again.
And so the cow is gonna run in a circle. And they tell us that the cow has a mass of 360 kilograms.
Tell you that was disgusting.
And the coefficient for the cow is
They don't have agility.
is 0.59. I did look that in the paper. Someone published a coefficient for friction for cow feet to different surfaces. Yes, I found a paper.
Wait,
What
what?
was the point of doing that kind of a study?
I don't know, I don't remember.
I assume it has to do
Found
something
out
with
pretty
that.
wow. It has to do with like how the flooring affects the cow's feet over time or something. Like wear and tear on the cow feet and the surface.
So maybe like a hoof front thing.
Oh, well, that would make sense.
It would make sense.
It's like a-
They tell us this cow is running at 13
Yeah.
miles per hour. And they wanna know what the radius of turn is. So when we know the cow is running, we know that static friction is holding us to the turn. This is the car taking a turn, but it's a cow.
It's a cow.
So.
That's compared to what you said that they moved for like 5 miles an hour or whatever, like, or kilometers an hour, yeah.
No, they think that is like actual running speed of like a cow can, if it's really panicked, run.
That's.
Anyway, so what we wanna look at is we wanna at solving this circular motion problem. So we know that the sum of the forces in the radial direction is mv squared over r. And so we know that this force here is the force of static friction, which is mv squared over r. Now the cow is running, I think they tell us it's like a flat surface, yeah. So there's a flat surface, and so on a flat surface, we sum the forces on the cow. Right, so here's our cow. And we know that this is normal and the weight, and because of this, we know the sum of the forces in the line is 0. So normal minus weight is 0. So the normal force is the weight. So our friction force is gonna be mu static times the normal, which in this case is the 0.59 times 360 times 9.8. For 1954, please.
2082.
Dang,
That's a lot of friction.
282,000.
2082.
20. Okay. Yeah. That's okay. 18 plus that, yeah, okay. Alright, so this is the force of static friction, that's gonna go here. So 2802 is equal to 360. Now, the only other thing we need to do is convert our V from miles per hour to meters per second. And the fastest way to do that is 4 nines. Right? So if you take your 13 miles per hour and you remember that there's about 1,600 meters in 1 mile. And then you remember in 1 hour, there's 3,600 seconds. This is 4 nines. So. And so 4 nines of that is 5.8. And so we put in our 5.8 squared, and R then is 3060 over 5.8 squared divided by 20. Questions? 5.8 meters. There are like 6 different or 5 different versions of that.
Conversions on the final, is it all good? Is we can.
You probably have to convert things. I don't remember if they're on there.
In standard or from like.
I
Like.
don't remember, honestly, I honestly don't remember if they're on there, to be honest. So if you wanna write a few of them on your sheet.
Just to be safe.
Yeah. Like if you want any other spot, like, 2.54 centimeters,
Oh,
an inch.
Those were
Like
on the sheet.
0.3048 meters, feet in a meter.
What do you anticipate to be the most missed section of this exam?
I can't say that. It's a good question, though, but I can't answer it.
Yes.
Yes.
The answer is yes.
The whole
You know.
Why? Because we all don't know what's going on.
I told you it's not.
I know.
Yes, you get that. I think it's gonna be.
He said it was on the last, so held on for that.
Yeah.
A real good point.
Yeah, I usually the fourth exam goes pretty well.
I think it's just because it was just the timing of everything.
That's what I said.
And we're all just like, we're done.
I
Let's
think-
go to break.
I think everyone, that was what it is everyone else had like not finals, but exams on Friday and Monday, and people just were done. That was it.
We were all just clocked out and just like, I don't want to
I
be here
thought
anymore.
about trying to move that exam to the week before Thanksgiving, like on that Wednesday evening.
Oh,
That
honestly,
way-
that probably, oh wait, no, it wouldn't, because I had like 4 other exams going on.
I already had 2 on Friday before, but I didn't include his, and
Right.
another one that Monday. So it was just 4 like that. Ironically, though, I did good on one of them. This one, it was but this one.
It wasn't because I wanted to be gone.
Yeah.
And they're like, I just want to go to Thanksgiving, I want to get out.
Sadly, the one that I did well on was not the exam I cared about. That was gonna be the easy exam.
Yeah.
Is there any other questions?
Well, that.
What height of building is to? In order to break.
They do have that problem that book about the feet breaking from falling from a certain distance.
I was gonna
It's a
say,
chapter 8 problem on Young's modulus.
How many newtons to break a human neck?
That I don't remember.
I don't
But you
have
can,
one.
there is a paper online.
Because I look like on Reddit, it says it's like between 20 and 32.
Yeah,
So it's
I can
It's
tell you
very-
it's not.
it's kind of a high number. It's a.
It seems how
They
much
said
pressure.
on average, like if you fall from like 10 feet, then enough to like break your
Yeah.
leg.
Well, that's the thing, like you can fall in your bathtub and snap your neck,
Yeah,
but
it just depends on how. Well, so remember, it's not just the force, it's also how the pressure. So like if you hit the edge of something, that same force is in it's a very narrow spot, it's a high pressure that can.
That's why, that's also what why Kevlar vests, like bullets, and the whole idea of a Kevlar vest is it spreads it out, but like arrowheads are very narrow points and they'll rip through.
Well, yeah, that's why they make armor piercing rounds, is because the round is designed to go between the Kevlar meshing. But even if you had Kevlar and you get hit,
It
there's
still
still a.
hurts.
Oh, yeah, because there's still a force of impact of the bullet, it's a collision problem, right? Because the bullet hits the Kevlar stops the bullet, but it's still, the Kevlar moves into hits you,
yeah,
yeah.
you get bruised.
Yeah, you can still have internal pain, you just aren't having
Yeah.
the ripping pressure.
Can you figure out the force it took to break my wrist when I fell off the paper?
If you need to strike the skull, yeah.
That's just.
There are no specifics.
I know that they do, but that is one of the problems, like you talk about people falling, it's a chapter 8 thing with the Young's modulus. And that's why they tell people like, oh, you should bend your legs when you're landing. So you, like they're springier, so you can absorb like the bigger.
I didn't land on my
That's why you landed on your wrist in a weird fashion.
I like was going down a hill and it wobbled. And then I think it was more I rolled on top of it.
Oh, rolled it.
Yeah. And it
You created torque.
It is very easy to break bone. It's so easy to break bone. No, unfortunately not.
I will say, I think that you should do